Hey everyone, time to finish breaking down the preprocessor, and today I'm going to tell you about macros that are already predefined and built into the preprocessor. A predefined macro is a macro that the compiler defines automatically even before your code starts being processed by the preprocessor. There are macros that are predefined by all compilers. Those are the ones we're going to talk about. And there are also macros that each compiler additionally defines for itself. I'm not going to cover those, but you can look up a list of those macros online yourself if you're really interested in or need that information. Let's start with the __C++ macro. This is a standard predefined macro that shows which version of the C++ standard the current translation unit is being compiled under. We'll talk more about this term in the next lesson, but for now, just think of it as a .cpp file. We still don't know how to create multiple .cpp files yet, so for now we're only dealing with one. So, __C++ is used for conditional compilation, checking standard support, compatibility between C++ 11, 14, 17, 20, 23, and writing portable libraries. Here's the first example. I want to print the value of this macro to the screen. Depending on the C++ standard, different numbers will be shown here. I wrote a small table here. This macro is represented by a number like this. The first 4 digits are the year the standard was adopted. The last 2 digits are the month it was adopted. And there's an L suffix at the end because it's a literal of type long. At the time of recording this lesson, when you create a C++ project, the default standard in the settings is C++ 14. So it would seem like we should see the number 2014-02L, but instead it shows 1997-11L. Why? Because specifically the Visual Studio compiler, MSVC, has had a long-standing issue with this macro, which makes it seem useless if you use this compiler because it always returns the oldest value. So what do? There are 2 options. The first option is to use the macro that this compiler provides instead, namely _MSVC_lang. That one actually returns different numbers depending on the project settings. Or you can go into the project settings, select C++, command line, additional options, and type this code here. So why do we need this macro? Thanks to it, we can check whether a certain standard is supported. If it is, then we can write code that works with that standard. Moving on to the next project, and the next macro __date__. This is a standard predefined macro that expands into a string literal containing the compilation date of the current file. The format is the following. The first 3 characters are the English abbreviation of the month, and the next 2 characters are the day, and the last 4 characters are the year. In the example below, I want to print the value of this macro to the screen. We'll see today's date. You can store the value of this literal wherever you want. This macro is usually used when you need to record the compilation date of some build version. The value of this macro depends on the day of compilation. Today it's one value, tomorrow it's another. This macro can often be found in build metadata, diagnosis, debug information, version banners, embedded software firmware, and internal tooling. Moving on to the next project, and the next macro __file__. This is a standard predefined macro that expands into a string literal containing the name of the current source file. Here, I want to print its value to the screen, and you can see that it shows the full path to our file, including its extension. It's usually used in logging, assertions, debugging, and diagnostics. For example, if you have a large project and you want to stop the program somewhere for specific input data inside a certain function, you can use this macro to indicate in which file the error occurred. This macro is encountered much more often than the previous ones. Moving on to the next project, and the next macro, line. This is a standard predefined macro that expands into an integer literal containing the current line number of the source file. Here, we'll see the value 5, because that's the exact line number where this macro is being used. If you move this line further down, the number will change. This macro is used in exactly the same places as file, to make it easier to locate where an error occurred. In other words, you can know not only the name of the file where something went wrong, but also the line number. Moving on to the next project and the next macro, time. This is a standard predefined macro that expands into a string literal containing the compilation time of the current translation unit. The format is the following: 2 characters for the hours, 2 characters for the minutes, and 2 characters for the seconds. Right now, I'll see this time, the time when this file was compiled. If we recompile this file using the Ctrl plus F7 keyboard shortcut, the time will change. And this macro is also used together with the previous macros for the same reasons: build information, version banners, embedded firmware, debug builds, and so on. But in the C++20 standard, an excellent tool appeared that replaces these things: std source location. To use it, you need to set the project standard to C++20 or higher, and then include the source location header in your file. std source location is a tool that lets you get the file name, line number, even the column number, and the function name at the point where this tool is called. There are still a lot of things here that you don't understand yet. First of all, there's still the std namespace, which you don't fully understand. I already said that it's just a named scope that contains a bunch of tools, and to use them, you need to write std followed by 2 colons. Source location is a structure. If you look at its definition, you'll probably be horrified, but many things there will already look familiar to you. For example, you can see a lot of macros, conditional compilation, and further below you can find the fields of the structure. We can see that it stores the line number, column number, file name, and function name. Now let's go back to our file. Here, I'm setting a default parameter by calling the current function. This is a static method, and you also don't know what that is yet. So for now, you can just think of it as a function. This function returns a structure object that will be tied specifically to this log function. Inside the function, we call different functions that belong to our structure. Structures can store not only fields, but also functions? Yes, they can, but I'll talk about that in other lessons. What matters here is that these functions return the values of all those fields we saw earlier. In the main function, we call this function and see the file name, line number, and function name. That's why in modern C++, people use this tool instead of file, line, and func, which we haven't talked about yet. I think now is the time. So __func __ is an exception in today's lesson because it's not a macro. It's an implicitly defined local constant that the compiler automatically creates inside every function, and it stores the name of the function itself. In this code, we have 3 functions. In each one, I want to print the value of this constant. Here, it's equal to this literal, and here it's equal to this one. It can only be used inside functions. It's usually used in the same places as the previous macros to point more precisely to where an error occurred. Moving on to the next macro. This one is a bit harder to understand. Let's break down 2 terms first. A hosted implementation is a normal, full runtime environment. For example, a program running on Windows, Linux, or Mac OS. A hosted implementation usually has a full standard library, a file system, an operating system, a main function, a heap memory, threads, which we'll talk about far in the future, and input-output streams. A freestanding implementation is a stripped-down environment. For example, a kernel, bootloader, embedded firmware, bare metal environment, game console SDK, or OS development. There may be no file system, no console, no threads, and not even a main function. And there's a macro that helps us understand which of these implementations we are currently in. If it's hosted, it returns 1. If it's freestanding, it returns 0. Very simple. Will you ever need this in practice? Most likely never. In C++ 17, the __std cpp _default _new alignment macro was added. Sounds scary. It shows the alignment guaranteed by the regular operator new. In simpler terms, this macro tells you what maximum normal alignment is guaranteed to be supported by the standard new without using special aligned overloads, although that probably wasn't any simpler. Anyway, on most modern platforms, it returns the value 16. Why can't this number even matter? Because sometimes require large alignment. And to properly explain this macro, we'd have to dive deep into alignment programming, where terms like align as, align off, and other scary things are used, and you don't know those yet. This macro is used in allocators, game engines, SIMD libraries, HPC, and low-level containers. So there's a small chance that you'll run into it while learning certain libraries. Let's move on to something simpler. In C++ 17, the __has_include macro was added. It tells you whether a specified file exists in the system so that it can be included. If the file exists, it returns 1. Otherwise, it returns 0. It's used to check for the existence of headers, write portable code, support different compilers, platforms, and adapt to different standard libraries. You can write the file name either inside angle brackets or regular quotes. There's also a macro that helps you find out whether the compiler supports a specific attribute. You don't know what attributes are yet. We'll cover them in a separate lesson. But if you ever see constructions like this in code, names surrounded by double square brackets, those are attributes. Different C++ standards introduced different attributes, and before using them, you can check whether they actually exist. If they do, you use them. If not, you use alternative code. For example, there's the noDiscard attribute, which increases the importance of a function's return value. I can call this function without storing its result anywhere, and the compiler won't complain about it. But if it's important not to ignore the return value, then you can use this attribute. And in that case, if you ignore the function's return value when calling it, the compiler will generate a warning. We'll cover this attribute and other attributes in much more detail in a separate lesson. There are also a huge number of macros that are defined if the compiler supports a specific language feature. They're called standard feature test macros. They start with __cpp_ followed by their names. For example, we can check whether the language supports lambdas. If it does, we can use them. We can also check whether it's possible to write conditions in the if statement that are evaluated at compile time. If yes, we use them. There are a lot of these macros, and I'm not going to list all of them. The point is that even if your compiler started supporting a certain standard and you heard somewhere that this standard is supposed to support some new language feature A, that doesn't necessarily mean your compiler supports that exact feature A. And to check whether that specific feature A exists, you use macros like this. And the last macros are library feature test macros. They let you check whether a specific library feature is available. They start with __cpp_lib_. Here's an example. In C++ 20, the format header was added. We can check whether it exists. If it does, we include it. Then we check again whether this function exists. If yes, we use it to print information. Otherwise, we use regular cout. There are also many macros like these. Now, the most important thing, there's and 99% chance that you will never use most of this information, but you might run into some of these macros somewhere. So it's still better to understand how they work in general. And with that, we can finish covering the preprocessor and move on to other C++ language topics. That's it for this lesson. Thanks for watching. If you enjoyed the video, you can leave a like, drop a comment, subscribe to the channel if you haven't already, become a channel member to get access to practical lessons, or support me via the link in the description or through YouTube's Thanks feature. See you in the next lessons. Goodbye.